Hi, I'm Alexandra Bejarano, a PhD student with the Mirror Lab at the Colorado School of Mines, and today I will be presenting on the impact of robot group presentation strategies on mental model formation. This work was done in collaboration with Samantha Reig from Carnegie Mellon. From a user's perspective, interactions with individual robots typically consist of robots with human-like mind-body identity associations, where one mind controls one body and presents one identity. However, interactions with groups of robots are more complex. There may be more minds, bodies, and identities involved, and the associations between them can be broken down and stray from human-like configurations. Recently, a number of researchers have highlighted the flexibility of the relationship between robot mind, body, and identity. This flexibility offers opportunities to design robot body, mind, and identity in different non-human-like ways that may be useful within human-robot interactions. But it also brings about a tension between how the concepts of mind, body, and identity are at the robot software level and how their relationships are perceived by humans at the user level. Specifically, a robot group can make use of an identity performance strategy to evoke certain user mental models that do not match the inner workings of the robot group at the software level. For instance, a robot group may present itself in such a way that a user may view the group as multiple individuals with distinct minds. But at the software level, the group is actually being controlled by a single mind. In his work on deconstructed trustee theory, Tom Williams points out that the distinction between different identity performance strategies is critical because the number of bodies and identities involved in a user's mental model dictates where and how they believe trust can be placed and how users allocate trust to different trust loci, be that the different robot identities and bodies presented. So, in this work, we sought to understand how different identity performance strategies used by robot groups might impact the mental models users form of robot groups and their constituent minds, bodies, and identities. We also aim to understand how those different strategies and the mental models they evoked might impact entitativity, a key group dynamics construct. We systematically explored how changes in different group identity observables might impact the mental models people develop of robot groups during initial human-robot introductions. To do so, we performed an online study in which participants viewed and reflected on animated storyboards across 42 conditions. We first identified these 5 key speech-based observables that may be leveraged at the user's level of abstraction to infer relationships between the minds, bodies, and identities of the robot group, and to construct corresponding mental representations. Speaking refers to who speaks and when, which may signify where and how cognition is distributed among the robot group. For instance, if a group of robots all spoke together at the same time, then this may indicate that a single mind is distributed across all robots. Self-reference refers to how an identity speaks of itself or the body it inhabits. This may lead to inferences about the presumed speaker and the relationship between that speaker and its body. For example, if a user used I am to introduce itself, one can see that the self is directly referenced and that the name following I am is associated to the speaker and its body. Other reference refers to how an identity speaks of other identities or the bodies they inhabit. This may lead to inferences about the relationship between the speaker and those other identities or bodies. For example, if a speaker refers to another body starting with "this is my," one may infer that the speaker owns that other body. Naming refers to the name used for oneself or another, be that a single individual or the overall group. This may lead to inferences about the relationship between the speaker and the other identities presented. And finally, name and voice distinctiveness was used to directly communicate body identity alignments through the assignment of either shared or unique names and voices. We used these observables to create a set of 42 robot group introduction storyboards. In each storyboard frame, one or more of the robots introduced themselves or was introduced with a self-reference and/or other reference and a given name and voice. For instance, in this storyboard frame, the group of robots speak at the same time, with the same voice, refer to themselves as part of a whole by using "we are," and use a single, shared, descriptive group name. Participants in our study viewed a subset of our 42 animated storyboards, and then answered a series of reflective open-ended prompts so that we could assess viewers' mental models of the robot groups. Participants were also asked to answer a series of closed-ended questions to assess robot group entitativity. We collected responses from 166 participants through Prolific. Each participant viewed a random set of 6 of the 42 storyboards. This produced a total of 1,112 responses for each of our measures. To analyze our qualitative data, we used a grounded theory-informed approach to identify the types of mental models people developed. We then used statistical analyses to examine the impact of each group identity observable on the types of mental models users formed and the impact of each observable and the mental models they evoked on entitativity. Our qualitative analysis revealed 2 fundamentally different taxonomies of mental models formed by users. The first we call intelligence distribution. Participants formed different mental models of the different actors they even perceived to exist and how and where the cognition, or the mind, of the robots was distributed. We found 3 main categories of intelligence distribution. Some participants developed a one-for-one mental model where each robot had a single identity or a single mind behind it. For example, some participants stated that they thought each robot body had a unique identity or seemed to be operating independently. Other participants developed a one-for-all mental model where all robot bodies had a single shared identity or a single mind behind them. For example, one participant said, "Riley is the mind behind the 3 interconnected units." And finally, some participants provided no evidence for either of these mental models. The second taxonomy of mental models we observed we call social relationships. Participants formed different mental models of the social relationships that they perceived to exist among the different actors they recognized. We found 12 main categories of social relationships, such as seeing the robots as collaborators, seeing one robot as the spokesperson for the others. These social relationships also included nuanced cases where the relationship perceived was one of parts of a whole, especially when users had developed a one-for-all intelligence distribution mental model. Our quantitative results suggested that all 5 group identity observables influenced participants' intelligence distribution mental models, resulting in huge differences in perceptions of entitativity. While we don't have time to go through the results, we found for each Q and each mental model, we generally observed that shared behavior and qualities led to more frequent formation of a one-for-all mental model, which led to increased entitativity. In contrast, unique behaviors and qualities led to more frequent formation of the one-for-one mental model, which led to decreased entitativity. And in contrast to intelligence distribution, our results suggested that only name and voice distinctiveness influenced participant social relationship mental models. This surprising asymmetry raises key questions for future work. Our work also yielded clear preliminary design recommendations for designers seeking to facilitate different intelligence distribution or social relationship mental models. 1. To evoke the one-for-all mental model, robots should be designed with shared qualities and collective behaviors. 2. To evoke the one-for-one mental model, robots should be designed with individual unique traits. 3. To evoke the individuals and collaborators' social relationship mental models, robots should be designed to each speak with a unique voice and have a unique name. 4. To evoke the R1 social relationship mental model, robots should be designed to speak with the same voice and have a shared name. 5. To evoke the supervisor-subordinate social relationship mental model, robot groups should be designed with only one robot being capable of speaking and having a name. And 6. To evoke the owner-ownee social relationship mental model, robots should be designed to speak with the same voice and have a shared name, or the group should be designed with only one robot being capable of speaking and having a name. Overall, in this work, we considered 5 group identity observables and demonstrated how these observables led observers to develop fundamentally different mental models of the intelligence distributions and social relationships of robot groups. Additionally, we demonstrated how variations in these observables and the mental models they evoked influence entitativity. Finally, I'd like to leave you with 2 key points to take away from this talk. 1, robots are mentally modeled differently than humans are, and theories from group social psychology need to be adapted to account for this fundamental difference. And 2, even a simple hello from a group of robots can have radically different types of influence on humans' mental models of the group based on how that introduction is presented. So, thank you for listening. For more details, please read our paper.